Often we'll want to calculate derivatives of our data. For example, if we've measured a position and we'd like to figure out what the velocity is or the acceleration. And we can estimate those derivatives if we've measured some data. We can estimate them numerically by just taking the change in the value divided by the change in time. And that'll be mathematically correct as long as the differences are small. Unfortunately, if we make these differences small and they have any uncertainty in them at all, we know that the differences are going to become really important in determining the uncertainty of the overall calculation of this derivative. So we're going to have to balance off making delta t small versus making delta t accurate, and likewise for the value on top. So let's see how this works out. We'll import some of the usual stuff. And now I'm going to say that I'm going to start off by saying that numerical differentiation is going to work really well on clean, evenly timed data. I sure hope this is what's going to happen. So let's assume that our code is reading in a value at some sample rate of rate samples per second. And the times at which it samples have some variability in them because it might be taking different execution paths through the code. For example, if statements could wind up doing different calculations. So we can get a nominal time base as an array of a whole lot of evenly spaced reading times. And that's what we're going to do down here. This nominal time base is a linear space that starts at 0 and goes up to the length of time that we've sampled for. We've set the sampling time equal to 3 seconds here. And it'll be divided into a number of steps that'll depend on the rate at which we're sampling per second times the number of seconds we sample for. So in this case, it's going to have, about 7,000 steps in it for that nominal time base. Once we've got that nominal time base, we can define some functions that'll estimate derivatives based on the simple difference values between the change in the value and the change in time between the two sample points that we look at. Now, to let us do this and make some sensible decisions, I've defined this function here called value. And it's just a trigonometric function with two sinusoids, and it returns a value that'll oscillate around 90 with a couple of sine waves here. I can analytically take the derivative of those sine waves, and I've just got two functions here that'll return the first derivative and the second derivative. So this is all straight from analytic math. No numerics going on here at all. Now down here, I'm going to calculate the difference-based derivative estimate by looking at what was the different values of v at different values of t. And I'll space my sampling out by at least one time step, probably some more. So for example, if I look down here, this is the value v of t plotted out over time. And if I examined it at this time and at this time, some time steps apart, then I could take this v minus this v, so that would be the difference there in the v value, divided by this time minus this time. That would be the difference t there in that value. So I've got dv dt, and taking those two together should give me a good estimate of the slope of the derivative. So what I'm doing here is I'm setting up an array to hold the results in, and then I'm going through the whole range of values for all of the time steps t. So 0 out to the length of time t. And if I'm not actually steps distance into the data, I can't make a calculation. So for example, if I'm going one step at a time, then I could calculate a derivative at step number 1, but not at step 0. So what this is doing is it's starting gracefully and it's saying, well, if I can't calculate it yet, estimate it as the first one that I can calculate it at. So if it's less than steps, just start from steps. Otherwise, you can just use the value as we go through the whole list. And it's saying that the derivative is going to be the value minus the value some steps before, divided by the time now, minus the time some steps before. And then it will return that value. So this is estimating the derivative. And we can have a look at what happens when we do that calculation. We're going to plot out first the analytic values so that we've got something to compare to. So these are just our functions, value, dv dt, d2v dt. That'll plot out the analytic value of the function and its derivatives. Next, I'm going to use that time base, and I'm going to calculate the numerical derivative for that time base and the value, going only one step at a time. And I'm going to divide it by 5 to scale it just so it fits on the same graph. And I'll label that as going through and doing the numerical value on just one step at a time. Now, I said that taking a really short time step might be problematic. So let's try taking a longer time step. Let's go 50 steps at a time and see what that derivative looks like. And finally, I'm going to take the second derivative by going through and taking the derivative by my numerical differentiation with the nominal time base of the derivative I already took of my value at that nominal time base, so that I'm taking the derivative of a derivative. I should get the second derivative with time. And again, I'm only doing it with one step. So let's run that. And what do we see comes out? Well, that's what the actual value is with time. And then we've got a derivative with time. That's this one. So it's positive when it's going up and negative when it's going down. So that's good. And 0 when it's at a minimum or a maximum. So that's good. The derivative's making sense. And I've got my orange line. I don't see an orange line here. That's because the orange line is right underneath the red line. It's so close that you can't even see the difference. The purple line is when I took 50 steps. And when I'm taking 50 time steps, I wind up with a value that lags behind a little bit. I'm reaching quite a ways back in time, and as a result, it's a little slower to pick up the information. So 50 time steps, probably more than I want to use. Finally, the second derivative, I've got a green one, which is this line, and I've got a brown one, which is also this line. So what I can see is that the numerical results follow the analytical results very accurately, even if I do only one time step. I've got good results, I've got no problems with round off, and they're very believable. That is provided that all of the data is clean, no noise, accurate, right out to a large number of decimal places, and that data is evenly timed, so I don't have any variabilities in my timing. It works beautifully. Now, what about if I have variable times between samples? I'm going to tell you right ahead of time that that isn't going to change things much. So we said before that we could assume our code read values at about rate samples per second, but now we're going to introduce this variable number of clock cycles that it could take longer or shorter each time. So we'll have our same nominal time, and now we'll get some actual times that the reading actually took place. We're going to force those to be an even number of microcontroller clock cycles apart, and we're going to have a random variation in the period in between. So the clock cycle rate for the Arduino is 16 million cycles of the clock per second, and I'm going to take that clock and divide by our sample rate, so that'll give me the number of clock ticks on the processor to go one time through the sample loop. And I'm going to say that the variation is about 1/8 of that time. So it's a fraction of a cycle. So that we can, and we could try different fractions to see what happened. But for now, let's make it 8 times through. And now I'm going to make t as a copy of the nominal time. I'm going to round it off to a discrete number of clock steps at 16 megahertz. And then I'm going to add a random number of clock ticks according to how big the variation can be. So, and then I'm going to divide by the clock rate to put it back into seconds. So now I've got t, which has some variable timing rather than the nice even timing of our nominal time base. And I'm going to calculate v as the value that we get for that, that collection of not quite evenly spaced times. Then I'm going to do the same things as I did before. I'm going to plot v of t, and lo and behold, v of t winds up looking exactly the same. I'm going to plot the derivative that I get and the second derivative that I get as a function of time. And we might see those a little more cleanly if we plotted them down here afterwards, so they'll be plotted on top. And I'm going to plot my derivatives, calculated both with 1 step and 50 steps. And sure enough, I see very much the same thing that I saw in the previous graph. And then I'm going to plot my second derivative, calculated the same way as I did before. And if I run that, well, lo and behold, it's doing pretty much exactly what it was doing before, except now that second derivative has got some noise in it. Not an awful lot of noise. You can still see pretty clearly what's going on, but it's picked up a bunch of noise. That's coming in because of this variability in the time steps. That's a little troubling. Well, let's have a look down here and see what our variability in the time steps looks like. So what I'm going to do now is I'm going to plot as a function of time the difference between our original nominal time base and the time base that we've got now, the one that has some variability in it, and see what that looks like. And I'm also going to plot the difference in time between one time step and the next time step. And what we'll see is that the difference in time between one time step and the next time step has some variability to it. And the difference between the nominal times and the variable time has some variability in it as well, about 1/8 of the total duration of time between samples. So those values are a little noisy, and that's just the time base that's got some noise in it, and that's leading to some noise up here in that second derivative. But all these values are still accurate. We haven't got any inaccuracy in the time yet. So let's see what happens if we don't know the time quite accurately. We know that micros and millis aren't completely accurate. Micros is pretty good. Millis is crummy, plus or minus 2 milliseconds. And we've looked at this kind of behavior in another video. So we've got these functions for micros and millis. We can get our time base and find out what we would read if we use the micros or the millis function. And down here, what I'm going to do is I'm going to calculate the time as if it had been reported by the millis function and the time as if it had been reported by the micros function. Then I'm going to compare the difference between our time base t and what millis recorded, and our time base t and what micros recorded. And I've amplified this by 100 times. So I can see very inaccurate with the millis function, not so bad, up to 4 microseconds off with the micros function. So now let's see what happens if we use these real time bases that we get from our micros and millis functions instead of using the actual correct real time base. So I'm going to go through the process again, plotting these numerical derivatives, but now I'm going to use the time base, first the millis time base, and then the micros time bases for all of these other calculations. And let's have a look and see what we get. So I've got my values. That still looks good. I've got first derivatives, and I've calculated them in a variety of different ways. For a start, I've got a first derivative that was actually calculated from my analytic functions, and that should be quite correct. So that's my first derivative here, giving me a nice straight line. Nice, well-behaved line. But if I go and calculate my first derivative with the millis function here, even if I take 13 steps, but I'm using this millis time base, I'm getting this blue stuff that's got some noise in it, and it's kind of oddly shaped noise. And let's see what happens if I take a different value for the number of steps here. Let's take 6. It's larger noise and the characteristics are different. If I take just 1, I got divide by 0, and I hardly got any points here for the velocity as calculated for the millis time base. That's because just about every time I'm looking at 2 adjacent time steps, I'm in the same number of milliseconds. So that's kind of problematic. So let's step back and make that one, say, 12 again. I'm pretty convinced that I don't want to use this millis-based timing. It's just doing weird stuff to me. So now let's try calculating with the micros-based timing, the one that's going to be more accurate. And sure enough, if I don't even plot this part, we'll ignore the millis time base now. I get really nice values for the value and for its first derivative, no matter how I calculate that first derivative, whether I calculate it with just 1 step or calculate it with 5 steps, as long as I'm using the microseconds-based time base. Now I can go and calculate that second derivative. Well, in here in the middle of this green stuff, we can see what we're getting out as a second derivative of the actual value divided by 50, and it's progressing on fairly smoothly. But here in green, if we only use 5 time steps calculating v double prime, the second derivative, based on the microseconds time base, we get this noise creeping in again. So I've got even more noise than I had before, and that's if I went with 5 time steps to do my initial guess. So what if I had done it with fewer time steps? Let's try it with 3. Larger noise, and if I try it with 1, the noise is really pretty big. So let's compare this graph, where we've got pretty high noise, with this graph back here, where we had lower noise, with this graph back here, where we had no visible noise at all. So we picked up a little noise in our numerical calculation because we had variable size time steps. We picked up even more noise in our calculation because those variable size time steps weren't known accurately. They were only known to the accuracy of our microsecond time base, which is only accurate to within 4 microseconds. So 4 microseconds doesn't seem like a long time, but it's creating a lot of difficulty for us here in trying to estimate this second derivative. So let's go back here and switch that one back to 5, just so that it matches up with what we said it should be. And with a 5-step gap, we're getting reasonably low noise in that second derivative. And finally, if we allow 30 time steps to go by before we take the value of our derivative in both the velocity and then calculating the acceleration, the first and second derivatives, then we get this line here in red. And this red line is actually pretty smooth, although it's lagging behind the actual behavior. So by averaging over a longer time period, by taking longer time step to do our derivatives, we got a smoother behavior, but we're not staying up to date. And so far, we've only got variabilities in our time base. We've still presumed that our actual measurements of the value are completely perfect. So let's keep that in mind. We'll go on in a later video and see what happens if the measured values we got weren't actually as good as they might be.